Hello dear students. In today's class, let us solve the NEET questions from the chapter atoms. So what is the first question here? When the electron in hydrogen atom jumps from the second orbit to the first orbit. Which orbit to which orbit? The second orbit to first orbit. So the second orbit I will take, that is N2, then it is N2 is equal to 2 because second orbit. And the first orbit N1, that can be taken as 1. So when the electron jumps from second orbit to first orbit, see here, when the electron in hydrogen atom jumps from second orbit to the first orbit, the wavelength of the radiation emitted is, so that is lambda. What is the wavelength of the emitted radiation? That is lambda. Then when the electron jumps from the third orbit to the first orbit, the wavelength of the radiation emitted is, means when the electron jumps from third orbit to the, here N2 can be taken as third orbit and N1 can be taken as first orbit. Because the electron jumps from third orbit to the first orbit, then what is the wavelength of the emitted radiation? That we have to find. So I will take the wavelength of the emitted radiation is lambda dash. Our aim is to find the lambda dash. Then how to solve this problem? Solution for this problem. Solution for the first question. See here, when the electron jumps from second orbit to first orbit, what is the wavelength of the emitted radiation? That is lambda. Then by using the Rydberg's formula, 1 by lambda is equal to Rydberg constant into 1 by n1 square minus 1 by n2 square. Okay, the electron jumps from which orbit to which orbit here? The electron jumps from second orbit to first orbit, means 2 to 1. Here 2 is nothing but N2 and 1 is nothing but N1. Okay, then I will substitute these two in this equation, then we will get. So here what is lambda? Lambda is nothing but the wavelength of the emitted radiation when the electron jumps from second orbit to first orbit, that is given. Okay, that is lambda. Then 1 by lambda is equal to R into 1 by N1 is 1, 1 by 1 square minus 1 by N2 is 2. Then 2 square. Then on solving this one, we will get, so 1 by 1 square is nothing but 1. Then 1 by 2 square is nothing but 1 by 4, because 2 square is 4. Then what is LCM here? LCM is 4. Then it is 4 and it is 1. Then 4 into 1, that is 4. 1 into 1, that is 1. Then it is 4 minus 1 divided by 4, then it is 3R divided by 4. Then by using this one, we are going to find the Rydberg constant. So what about Rydberg constant here? I will take this 3 by 4 to the left hand side. What happens? I will take, so it is 1 by lambda. 1 by lambda is equal to 3 into R by 4. Then R is equal to, by using this one, we are going to find the Rydberg constant. Okay, so here R is equal to 4. This 4 comes to the numerator and 3 comes to the denominator. 4 by 3, already lambda is in denominator, then 4 by 3 into lambda. Okay, then 4 by 3 lambda, it is the Rydberg constant when the electron jumps from second orbit to first orbit. So when the electron jumps from third orbit to the first orbit, then what is the wavelength of the emitted radiation? That we have to find. So when the electron jumps from which orbit to which orbit here? That is from third orbit to first orbit. So when the electron jumps from second orbit to first orbit, we determined the Rydberg constant. Okay, then when the electron jumps from third orbit to first orbit, then what is the wavelength of the emitted radiation? So I will take the wavelength of the emitted radiation is lambda dash. 1 by lambda dash is equal to R into 1 by N1 square minus 1 by N2 square. Then, so here the electron jumps from which orbit to which orbit? That is from third orbit to first orbit. So here first orbit is 1, then the higher orbit is, that is 3. Then the electron jumps from higher orbit to lower orbit. Then R into 1 by 1 square minus 1 by 3 square. Then on solving this one, we will get 1 by 1 square is 1 minus 1 by 9. 3 square is 9. So what is LCM here? LCM is 9. LCM is 9, then it is 9 minus of 1. Then, so it is 8 into r divided by 9. Then it is 1 by lambda dash. 1 by lambda dash. Then we need a lambda dash. What we required now? We required lambda dash. Just interchanging numerators and denominators on both sides. I will take this lambda dash to the numerator and 1 to the denominator. That is lambda dash divided by 1. And 9 to the numerator and 8 into r to the denominator. So that is 9 by 8 into r. 8 into r. Then what is r here? R is nothing but 4 by 3 lambda. 9 by 8, r is nothing but here 4 by 3 into 4 by 3 lambda. Then this 3 lambda taken to the numerator, because this 3 lambda is in denominator, that comes to the numerator. Then it is 9 into 3 lambda, then divided by 8 into 4, that is 32. Then 9 3s are 27, 27 into lambda divided by 32. Then it is the wavelength of the emitted radiation when the electron jumps from which orbit to which orbit? That is from third orbit to. Now second question. The ratio of the largest to the shortest wavelength in Balmer series of hydrogen spectra is. Okay. See here. What we have to find here? The ratio of largest and shortest wavelength in Balmer series means we have to find lambda L by lambda S. So largest wavelength, lambda L means here largest wavelength, lambda S means here shortest wavelength. And one more thing, listen here, which is the given series? In the problem, Balmer series is given. What is the ground orbit in the Balmer series? That is N1 is equal to 2. Then which is the ground orbit in the Lehman series? That is first orbit, that is N1 is equal to 1. Already you know that. So which is the ground orbit in the Lehman series? First orbit. And which is the ground orbit in the Balmer series? Second orbit. Okay. And now, when we get the largest wavelength, only when the transition of an electron from nearest orbit to the ground orbit. So, which is nearest orbit for the second orbit in the Balmer series? That is third orbit. When the electron jumps from third orbit to second orbit, we will get the largest wavelength. And when we get the shortest wavelength, we will get the shortest wavelength only when the transition of an electron from infinite orbit to the ground orbit in the given series. Means here, in case of Balmer series, we will get the shortest wavelength only when the transition of an electron from infinite orbit to the second orbit. First we have to find the largest wavelength, and next we have to find the shortest wavelength, and we have to take the ratio of them. Then second one, largest wavelength. Largest wavelength. So in case of which series? Balmer series. Then 1 by lambda L is equal to R into 1 by N1 square minus 1 by N2 square. Then when we will get the largest wavelength, only when the transition of an electron from nearest orbit to the ground orbit in the given series. So which is the ground orbit in the Balmer series? That is second orbit. And which is the nearest orbit for the second orbit? That is third orbit. If the electron jumps from third orbit to second orbit, we will get the largest wavelength of the emitted spectral line or emitted electromagnetic radiation. Then I will put these two values in this equation. Then we will get 1 by lambda L is equal to R into 1 by N1 square. N1 square means 2 square. I will write directly. That is 1 by 4. Then N2 square means 3 square. That is 1 by 9. What is LCM? LCM is the 36 because 4 9s are 36. LCM is 36. 9 4s are 36 and 4 9s are 36 and 9 4s are 36. Then 9 into 1, that is 9, minus 4 into 1, that is 4. Then 9 minus of 4, that is 5. Then it is 5 into R divided by 36. Then it is 1 by lambda L. But we required lambda L because we have to find lambda L. Then, so just interchange the numerator and denominators on both sides. Okay, I will take this lambda L to the numerator and 1 to the denominator. That becomes lambda L by 1. So lambda L by 1 is nothing but that is lambda L. Okay, then 5r divided by 36 means here I will take 36 to the numerator and 5r to the denominator. That is 36 divided by 5 into r, 5 into r. Then we got the largest wavelength in the Balmer series. Then the shortest wavelength. We will get the shortest wavelength only when the transition of an electron from the shortest wavelength only when the transition of an electron from here the ground orbit in the Balmer series, that is fixed, that is second orbit. And for the shortest wavelength, the transition of an electron should be from infinite orbit to the ground orbit in the given series. Means here the higher orbit is infinite. Higher orbit is infinite. Again, by using this formula, we will get 1 by lambda s. Lambda s means here shortest wavelength. Lambda L means here largest wavelength. Then r into 1 by n1 square minus 1 by n2 square. On substituting the values, r 1 by n1 square is nothing but here that is 2 square, means that is 4, 1 by 4. Then n2 square means here 1 by infinity square, that is 1 by infinity, 1 by infinity is 0. Then we got the answer is r by 4. It is the shortest wavelength, the reciprocal of shortest wavelength. But what we require now? Lambda s. Just interchanging numerators and denominators on both sides. Then lambda s is equal to 4 by r. Then taking the ratios of them, I will take it is equation 1 and it is equation 2. So let us divide the equation 1 by equation 2. Then we will get the ratio of largest wavelength and shortest wavelength. Dividing equation 1 by equation 2. Then left hand side of equation 1, that is lambda L, divided by left hand side of equation 2, that is lambda S, is equal to right hand side of equation 1, that is 36 by 5r, 36 by 5 into r, whole divided by right hand side of equation 2, that is 4 by r, that is 4 by r. Then we can write 36 divided by 5r. Then this r comes to the numerator, because r is in denominator, that comes to the numerator, into r by 4. Then what get cancelled? R get cancel. Then 4 9s are 36. Then it is 9 by 5. 9 by 5. Then what is the ratio of the largest wavelength and shortest wavelength here in the Balmer series? That is 9 by 5. So try yourself in case of Lehman series, in case of Bastian series, in case of bracket series, and also Peepand series. So find the ratio of largest wavelength and shortest wavelength in Lehman series. Okay, this is the work for you. And find the ratio of largest wavelength and shortest wavelength in case of Bastian series, bracket series, and also Peepand series. Next, question number 3. An electron in a hydrogen atom makes transition N1 to N2. So from where to where there is a transition of an electron, that is from N1 to N2. Then where N1 and N2 are the principal quantum numbers of the states. Assume the Bohr's model to be valid. The time period of the electron in the initial state is 8 times to that of final state. What it's meaning here? The time period of the electron in the initial state. Which is the initial state here? The initial state is N1. Okay. The time period in initial state is 8 times of the time period of the electron in the final state. Then what is the time period of the electron in the final state? That is T. So listen here. Let us assume the time period of the electron in the final state is T, but the time period of the electron in the initial state is 8 times of the time period of the electron in the final state. Which is the final state here? N2 is the final state and N1 is the initial state. Then what is our question? Our question is to find the ratio of N1 and N2. Already we know that how the time period is related to the principal quantum number. That is directly proportional to the cube of principal quantum number. See here. So third one, the time period is directly proportional to the cube of principal quantum number and inversely proportional to the square of atomic number or the number of protons present in the nucleus of the atom. Then T is directly proportional to n cube and inversely proportional to z square. Then hydrogen atom is given. Then how many protons present in the hydrogen nucleus? That is only one proton. Then I will remove this proportionality by using the constant, that is T is equal to constant into n cube divided by z square. But for the hydrogen atom, z value is how much? 1. Z value is 1 for which atom? This is for the hydrogen atom, because there is only one proton present in the hydrogen nucleus. Then, so in case of first state, the time period of the electron is that can be taken as T1, that is equal to constant into n1 cube. Then what is the time period of the electron in the final state? Which is the final state here? N2 is the final state. Then T2 is equal to constant into N2 cube. Take the ratios of them. Then we will get N1 by N2. Then that is T1 by T2. T1 by T2 is equal to, so constant get cancel. Then n1 cube divided by n2 cube. Then what is the time period of the electron in the initial state? That is the 8 times of the time period of the electron in the final state. That is 8t. And what is the time period of the electron in the final state? That can be taken as t. That is equal to n1 cube divided by n2 cube. Then here t get cancel. Then n1 cube divided by n2 cube is equal to 8 by 1. 8 by 1, otherwise you can write 8 only. Then n1 by n2 cube can be written as n1 by n2 whole cube. n1 by n2 whole cube. Okay, already you know that. n1 cube divided by n2 cube can be written as n1 by n2 whole cube. Then it is 8 by 1. I will take this cube to the right hand side, that becomes cube root. Then n1 by n2, cube root of 8 is 2 and cube root of 1 is 1. Then it is 2:1. So what is the answer here? 2:1. The ratio of n1 and n2 is 2:1. So next, fourth question. Any radiation in the ultraviolet region of hydrogen spectrum is able to eject the photoelectron from a metal. Then maximum value of the threshold wavelength is lambda is equal to 1 by r is equal to 911 angstrom. Means any radiation in the ultraviolet region of hydrogen spectrum is able to eject the electron from the metal. Means the photoelectric emission is possible by using the any radiation in the ultraviolet region of hydrogen spectrum. So ultraviolet region means here which region? That is Lyman series. Okay, that is called Lyman series. The maximum value of threshold wavelength is lambda is equal to 1 by r is equal to 911 angstrom. Then the frequency of the metal is, means we require the threshold frequency for the metal for the photoelectric emission. So here what is given? The threshold wavelength is given. That threshold wavelength is represented by lambda naught. But in your question that is given by lambda. So that lambda naught is equal to 1 by r is equal to 911 angstrom. Then I will write lambda naught is equal to 911 into 10 to the power of minus 10 meter. So angstrom to meter I will write. Then what is the relation between the wavelength and frequency? If we know the wavelength, how to find the frequency? So that is by the relation nu is equal to c by lambda. Then that is nu naught is equal to c by lambda naught. What is the value of c? The value of c is 3 into 10 to the power of 8. So what is lambda naught given? That is 911 into 10 to the power of minus 10. Then 3 by 911, that is 0.00329. 0.00329. I will take this 10 raised to minus 10 to the numerator, that becomes 10 to the power of plus 10. 10 to the power of plus 10 into 10 to the power of 8, that is 10 to the power of 18. That is 10 to the power of 18. Then what is the unit of frequency here? Unit of frequency is hertz. Then, but we required before the decimal point one non-zero digit. Means I will displace the decimal point after how many digits here? 1, 2, 3. In which direction? Right direction. Then we can write 3.29. So after how many digits the decimal point is displaced here? 3 digits. In which direction? Right direction. I will write that is 10 to the power of minus 3. If we displace the decimal point in right direction, we will get 10 to the power of minus. If we displace the decimal point in left direction, we will get 10 to the power of plus. But here the displacement of the decimal point is in which direction? That is in right direction. Means after how many digits the decimal point is displaced? 3 digits. That is why 10 to the power of minus 3. Already 10 to the power of 18 is there. Then 3.29 can be written as 3.3, rounded figure. Then 10 to the power of 18 into 10 to the power of minus 3, that is 10 to the power of 15. 10 to the power of 15 hertz. This is the answer. This is the threshold frequency required for the photoelectric emission from the given metal. Okay. So how to find the frequency here? If we know the wavelength, by using the formula, that is nu is equal to C by lambda. It is the relation now. Then how to find the unit here? So 1 hertz is nothing but per second. Is it right? Okay. Then the speed of light can be measured in meter per second and wavelength is measured in meter. Then meter get cancelled. Then what remaining now? Per second remaining. So per second is nothing but hertz. Then what is the unit of frequency here? Hertz. Okay. So this is the solution for the given question.